Imagine an object, way out in the cosmic expanse. This isn't just any old celestial body. This is a star, a colossal ball of matter, but it's spinning at a rate that's almost impossible to wrap your head around. Picture a kitchen blender, aircraft turbine, its blades a total blur and faster than anything you can imagine. Now, imagine something vastly larger, a stellar giant, rotating not just dozens, but an incredible 707 times every single second. This is the reality for a star named Pulsar J09520607. It's a celestial marvel that's not just putting on an amazing cosmic show, it's also a ticking time bomb. It's on an unstoppable, one-way trip, a path that ends with one of the universe's most mysterious and powerful objects, a black hole. This isn't sci-fi, folks. This is the breathtaking reality of astrophysics, and we're about to dive right into its heart. Way out in the constellation sextants, somewhere between 3,200 and 5,700 light-years from us, there's Pulsar J09520607. Now, this isn't your average star, like our sun, just calmly burning fuel.
Only about 10 miles across, and yet they contain the mass of at least the sun, or even sometimes twice the sun.
Pulsar J09520607 is a pulsar, a very specific and incredibly extreme kind of neutron star. So, what exactly is a pulsar? And what's a neutron star? Let's break it down. When a really massive star, way bigger than our sun, hits the end of its life, it doesn't just fizzle out. Nope, it goes out with a bang, a massive explosion called a supernova.
When a large star dies, it will end its life as a supernova with a crazy big explosion. And the pulsar is what's left behind.
What's left after this stellar fireworks show is an unbelievably dense core. Cram 1.5 times the mass of our entire sun into a ball just 10 to 20 kilometers, or 6 to 12 miles, wide. That's about the size of a city. The gravity is so intense that protons and electrons get crushed together to form neutrons, hence the name neutron star. A single teaspoon of neutron star stuff would weigh billions of tons on Earth. This is matter squeezed to its absolute limit, just a hair's breadth away from becoming a black hole. Pulsars are a special breed of neutron star. They're highly magnetized and spin incredibly fast. From their magnetic poles, they shoot out powerful beams of electromagnetic radiation, radio waves, X-rays, even gamma rays. As the neutron star spins, these beams sweep across space, just like a lighthouse beam. If one of these beams happens to sweep past Earth, our telescopes pick up a regular pulse of radiation. And that's where the name pulsar comes from, a pulsating star. Now, among all the known pulsars, Pulsar J09520607 is a real champ, breaking records left and right. Its spin rate of 707 times per second, meaning it takes just 1.41 milliseconds to do a full rotation, makes it the second fastest spinning pulsar ever found, and the fastest one we know of in the main disk of our Milky Way galaxy. To give you some perspective, its equator is zipping along at about 14% of the speed of light. If it were any bigger, or spinning much faster, the sheer centrifugal force would rip it to shreds. But its incredible speed isn't its only claim to fame. As of 2022, Pulsar J09520607 also holds the title for the most massive neutron star known. It tips the scales at about 2.35 times the mass of our sun, give or take about 0.17 solar masses. That's a huge deal because there's a theoretical limit to how massive a neutron star can get before it just can't hold itself up anymore against its own gravity. This is called the Tolman-Oppenheimer-Fokoff limit. And Pulsar J09520607? It's teetering dangerously close to this edge. It's a celestial object pushed to the absolute extremes of physics, a ticking cosmic clock counting down to an unavoidable transformation. Its very existence pushes our understanding of matter under the most intense pressures imaginable, offering a unique laboratory to test the very fabric of physics. A star spinning 707 times a second? Seriously, how does any object, especially one with more than twice the sun's mass, get going that fast? The answer lies in a dramatic, and kind of gruesome, cosmic dance, stellar cannibalism. Pulsar J09520607 isn't just any pulsar. It's classified as a black widow pulsar. And yes, the name is as sinister as it sounds. It refers to a specific type of millisecond pulsar that has a companion star. And, true to its namesake, the black widow pulsar has a pretty destructive relationship with its partner. Here's the story of how it likely happened. When the neutron star was first born from a supernova, it was probably spinning fast, but not this incredibly fast. The extreme acceleration came from its companion. Over millions, maybe even billions of years, the powerful gravity of the neutron star started siphoning material, gas and plasma, from its less dense companion star. This process is called accretion. As this stolen matter spirals in towards the neutron star, it forms an accretion disk, a swirling vortex of superheated gas. Think of water spiraling down a drain, but on a cosmic scale and with unimaginably higher energies. The key thing here is that this infalling matter carries angular momentum with it. Just like an ice skater spins faster when they pull their arms in, the neutron star's rotation rate dramatically increases as it accretes mass and angular momentum from its companion. This spin-up process can take a very, very long time, but the results are spectacular, creating these millisecond pulsars that spin hundreds of times a second. In the case of Pulsar J09520607, it's thought to have gobbled up almost an entire sun's worth of material from its unfortunate companion. This relentless feeding has not only spun it up to its current incredible speed but has also drastically whittled down its partner. The companion star of Pulsar J09520607 is now just a tiny remnant of its former self, shrunk to less than 20 times the mass of Jupiter. It's more like a giant planet than a full-fledged star. It orbits the pulsar every 6.4 hours, and the side facing the pulsar gets blasted by intense radiation, heating it to around 6,200 Kelvin, hot enough for powerful telescopes like the Keck on Mauna Kea to faintly detect it. The intense radiation and particle winds blasting from the pulsar, a result of its rapid spin and magnetic field, continue to erode the companion star, effectively evaporating it over time. This is the black widow behavior. The pulsar, having gained its incredible spin and mass by consuming its partner, is now slowly destroying what little remains. So, what keeps this super spinner from just flying apart? Pure, unadulterated gravity. As we've said, neutron stars are extraordinarily dense. The gravitational force at the surface of a neutron star is hundreds of billions of times stronger than Earth's. This immense gravity is what holds the star together, even as it spins at a significant fraction of light speed. But it's a delicate balancing act. The star's structure is supported against total gravitational collapse by something called neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being squeezed too closely together. But even that pressure has a breaking point. As Pulsar J09520607 continues to accrete mass, or even if the accretion has mostly stopped, its total mass is inching closer and closer to that critical Tolman-Oppenheimer-Fokoff limit. That's the ticking clock. Every particle added, every slight shift in its internal structure, brings it closer to the point where neutron degeneracy pressure can no longer win the battle against overwhelming gravity. Here's a cool detail: for a millisecond pulsar like Pulsar J09520607, its surface magnetic field is remarkably weak, about 61 million Gauss. That sounds like a lot, but it's over 10,000 times weaker than typical, slower spinning pulsars, which can have magnetic fields quadrillions of times stronger than Earth's. Scientists think the act of gobbling up its neighbor actually weakened or buried its magnetic field over time. This low magnetic field is typical of these superfast, recycled pulsars. The journey of Pulsar J09520607 to become a speedster is a wild story of cosmic theft and blistering acceleration, all setting the stage for an even more dramatic final act. This star, Pulsar J09520607, isn't just a weird curiosity. It's telling us something profound about physics and conditions we can't even dream of creating here on Earth. This single object lets scientists probe the very nature of matter at densities so extreme they challenge our basic understanding. So, let's get into the nitty-gritty of the forces at play in this cosmic spinning top. First up, as we mentioned, is that mind-blowing gravity, a result of packing 2.35 solar masses into a sphere only about 12 kilometers across. This creates a gravitational well so deep that the escape velocity from its surface is a hefty chunk of the speed of light. It's this gravity that holds the star together, stopping its rapid spin from flinging it apart. Fighting back against this immense gravity is neutron degeneracy pressure. This is a weird quantum effect. The Pauli exclusion principle basically says that no two fermions, like neutrons, can be in the same quantum state in the same place at the same time. Think of neutrons as grumpy introverts. They really don't like being squashed together too tightly. In the superdense interior of a neutron star, this resistance to further compression generates an outward pressure, which, for most neutron stars, is enough to stop further gravitational collapse. But this pressure isn't all-powerful. There's a maximum mass, that Tolman-Oppenheimer-Foulkhoff (TOV) limit we keep mentioning, beyond which even neutron degeneracy pressure is overwhelmed. Current guesses for the TOV limit are somewhere between 2.2 to 2.9 solar masses. Figuring out that exact limit is tricky because it depends on how matter behaves when it's squeezed that tight, something called its equation of state. Our star, Pulsar J09520607, at 2.35, plus or minus 0.17, solar masses, is really pushing it. Just by existing, it helps scientists fine-tune their models for this equation of state. If a neutron star can be this massive, it means the stuff inside it must be stiffer. It resists being squashed more than we might have thought. And what is that stuff inside? We call them neutron stars, but their cores might be home to even weirder particles, like hyperons, or maybe even a soup of deconfined quarks, the fundamental bits that make up neutrons. If the equation of state were too soft, a star this massive couldn't exist. It would have already collapsed. Then you've got the centrifugal force from all that spinning. At 707 rotations a second, the material at the star's equator is feeling a massive outward fling. This actually helps a bit against gravity, meaning a spinning neutron star can hold a little more mass before it collapses than a stationary one. Some models even suggest that spinning neutron stars could potentially reach up to 2.93 solar masses. Don't forget the star's actual structure. The inside is a bizarre, superdense fluid, but the outer kilometer or so is thought to be a solid crust, made of a lattice of atomic nuclei and free electrons. This crust is incredibly strong, billions of times stronger than steel. But even that supercrust is under massive strain from the rapid rotation and the intense gravity. Some theories suggest that the maximum spin rate of neutron stars might be limited by how much their crusts can take. As a neutron star spins, it bulges at the equator. If this bulge gets too extreme, the crust could crack. This might even cause the star to emit continuous gravitational waves, which could slow it down. For Pulsar J09520607, its spin is already in the zone where these crustal stresses are a big deal. Another subtle but constant force is radiation. Pulsars, by their nature, radiate energy. Those beams they shoot out carry away energy and angular momentum, making the pulsar gradually spin down over vast amounts of time. For Pulsar J09520607, this spin-down rate is incredibly tiny, less than 4.6 times 10 to the power of minus 21 seconds per second. This super slow spin-down, along with its weak magnetic field, is typical for these recycled millisecond pulsars that got spun up by their companions. It suggests the pulsar system is around 4.9 billion years old, meaning it's been spinning this fast for a very long time. But the real ticking clock here isn't just about spinning down, it's about its mass. The crucial thing pushing Pulsar J09520607 towards its end is its closeness to that TOV limit. If it were to grab even a tiny bit more mass from its companion, if that's still happening, or if its internal structure were to shift just so, the delicate balance would be broken. Gravity would finally win the ultimate tug-of-war. Neutron degeneracy pressure would fail. The star would begin an unstoppable collapse. And then, it happens. Maybe one last wisp of gas from its poor, shredded companion star adds that final, fatal bit of mass. Or perhaps a subtle shift within its super-dense core pushes it over the edge. Whatever the exact trigger, Pulsar J09520607, the star that spun 707 times a second, the most massive neutron star known, finally gives in. It crosses that line, the Tolman-Oppenheimer-Fokoff limit. What follows is one of the universe's most extreme and mind-blowing events. A black hole is born. That neutron degeneracy pressure? It fails. Instantly. Catastrophically. Without this outward force holding it up, the star's immense gravity takes complete control. All 2.35 solar masses begin to implode. There are no other known forces in the universe that can stop this collapse. Picture the star, already tiny at around 12 kilometers across, now shrinking at an insane, terrifying speed. Everything inside is crushed beyond anything we can imagine. Protons, electrons, even the neutrons that once defined it, are squeezed into an ever smaller space. The density skyrockets, heading towards infinity. As the star collapses, a critical boundary forms around it, the event horizon. The point of no return. For a non-rotating black hole of Pulsar J09520607's mass, around 2.35 solar masses, this event horizon, also called the Schwarzschild radius, would be about 7 kilometers in radius. Once the collapsing star material shrinks past this boundary, it's effectively gone from our observable universe. Nothing, not even light, can escape the gravitational pull from inside the event horizon. To us, it's like the star just blinks out of existence, leaving only its gravitational influence behind. The formation of the event horizon is a defining moment. It's a one-way door that forever separates the inside of the black hole from the rest of space-time. Light emitted from the surface of the star just before it crosses the event horizon would be infinitely redshifted, its wavelength stretched to infinity, making it impossible to detect. From way out here, thanks to Einstein's relativity and extreme time dilation, it would look like the collapse freezes at the event horizon, the star's light just fading away over an extended period. But for the star's matter itself, the journey isn't over. Inside the event horizon, all paths, all possible routes for matter and light, lead inevitably inwards, towards the center. The collapse continues until, according to our current understanding based on Einstein's theory of general relativity, all the star's mass is crushed into an infinitely small point of infinite density, a singularity. At the singularity, our known laws of physics just stop working. Density, temperature, and the curvature of spacetime all become infinite. General relativity, our best theory of gravity, can't describe what's happening there. To truly understand the singularity, we'd need a new theory, something called quantum gravity, a theory that successfully combines general relativity with quantum mechanics, which physicists have been working on for decades. What about all that incredible spin? As the star collapses, the conservation of angular momentum means its spin rate would try to increase even further, potentially to truly mind-boggling levels. However, black holes are surprisingly simple, according to the no-hair theorem. This theorem says that a stable black hole is defined by only three things: its mass, its electric charge, which is usually tiny for astrophysical black holes, and its angular momentum, its spin. All other details, all the hair, like what it was made of originally, its magnetic field, the complex details of its structure, are lost, swallowed by the event horizon. So, the new black hole will inherit the mass of Pulsar J09520607 and a significant amount of its angular momentum, becoming what we call a spinning Kerr black hole. The star's magnetic field, once responsible for its lighthouse beams, would be largely dissipated or swallowed. While magnetic fields can exist around a black hole, especially in an accretion disk if it's still feeding, the field that belonged to the pulsar is effectively gone, absorbed into the black hole. This collapse itself might not be completely silent in all respects. The rapid rearrangement of such a massive, dense object could, in theory, generate gravitational waves, ripples in the fabric of spacetime itself. Detecting such waves from an individual pulsar collapse would be incredibly challenging with current technology, given the likely distances, but they represent a potential way to see such an event. The climax of Pulsar J09520607's life isn't a slow fade-out, but a sudden, definitive transformation from an extreme star to an even more extreme gravitational entity. It's a point where matter as we know it stops existing in any recognizable form, crushed into a point that defies our current physics, hidden forever behind a veil from which nothing can return. And just like that, it's done. Where that super-fast pulsar used to spin with furious speed, there now lurks a brand new black hole, a silent testament to gravity's ultimate victory. What happens immediately after this transformation? The biggest change? Spacetime itself around it is warped dramatically. The gravitational field around where the pulsar used to be is now that of a black hole with about 2.35 solar masses. Far away, its gravity feels the same. If our sun suddenly became a black hole of the same mass, our orbit wouldn't change, though thankfully, that can't happen to our star. But get close, and it's a whole different ballgame. The event horizon, now a real boundary about 7 kilometers in radius, means a new reality. Anything crossing it, stray gas, an unlucky asteroid, or even light, is lost forever. And the poor companion star, the one that helped spin up Pulsar J09520607 and ultimately led to its doom? It's now orbiting a black hole, following the laws of gravity. The good news for the companion, if you can call it that, is that the brutal radiation and particle wind from the pulsar have stopped abruptly. The Black Widow isn't actively biting in the same way anymore. Instead, the companion might now slowly feed the black hole if it gets close enough for the black hole's tidal forces to pull material off it, possibly forming a new, more conventional accretion disk. If such a disk forms, it could light up with X-rays as material heats up. However, given the companion's tiny mass, this accretion might be minimal. The companion, already a shadow of its former stellar self, might just continue its lonely orbit around this dark, silent giant. The collapse into a black hole is a hugely energetic event, at least in terms of the gravitational potential energy released. As mentioned, this rapid change could generate a burst of gravitational waves, rippling out at the speed of light, carrying information about the pulsar's final moments. Detecting such a burst from a single stellar mass black hole forming in our galaxy is a major goal for observatories like LIGO and Virgo. Each detection would be priceless for testing general relativity and understanding how black holes form. Any cloud of particles, a pulsar wind nebula, that might have existed around pulsar J09520607 when it was an active pulsar? Gone. Swept clean, as the energy source for such a nebula has vanished. One of the most significant immediate changes is that the pulsed emissions are over. The lighthouse is out. The regular radio, X-ray, and gamma-ray pulses that defined pulsar J09520607 are gone forever. Telescopes that once picked up its rhythmic beat every 1.41 milliseconds will now detect only silence from that spot, or perhaps the faint glow of an accretion disk if material is still falling in. For astronomers who studied it, its death as a pulsar is the end of an era for a unique celestial lab. That magnetic field, so key to the pulsar's beams, is also fundamentally changed. As the star collapsed, the magnetic field lines would have been dragged in and massively compressed. However, the no-hair theorem means the black hole itself doesn't have its own complex magnetic field like the neutron star did. The energy from the pulsar's magnetic field was either radiated away during the collapse or, more likely, absorbed by the black hole. Any magnetic fields near the black hole now would likely come from an accretion disk, not the black hole itself. In the grand scheme of things in our galaxy, the birth of a single stellar mass black hole like this is a pretty spectacular event, but not incredibly rare. It doesn't send shockwaves that disrupt distant star systems. Its direct gravitational pull is localized. However, each such event adds to the population of black holes in the Milky Way, and these objects play a crucial role in how galaxies evolve over cosmic time. So, we've gone from a superactive, radiating object to something much quieter, but with an even more powerful, all-consuming gravitational grip. The cosmic spinning top has wound down, not into peacefulness, but into a different kind of extreme. So, this star turning into a black hole is a huge cosmic event. But what does it really mean for us, and should we be worried? First things first, don't panic. Pulsar J09520607 is thousands of light years away from Earth, somewhere between 3,200 and 5,700 light years. At that immense distance, its collapse into a black hole poses absolutely no direct threat to our solar system or life on Earth. The gravitational effects of a stellar mass black hole are only really significant right up close. Even if a nearby star did this, and none are about to in a way that would affect us, the big danger would have been the supernova explosion that happened billions of years ago to create the neutron star in the first place. The collapse into a black hole is an implosion, not an explosion flinging dangerous stuff across space. So, we can watch these cosmic dramas with awe, not alarm. They're a natural, if extreme, part of how massive stars live and die. The real importance of stars like Pulsar J09520607, and what happens to them, is what they teach us. Objects like this are invaluable cosmic laboratories for testing the limits of our physics. Its record-breaking mass, at 2.35 solar masses, pushed right up against the theoretical maximum for a neutron star. This gives scientists crucial data to help pin down the equation of state of matter at nuclear and even supernuclear densities. Understanding how matter behaves under such extreme pressures, conditions far beyond anything we can create on Earth, is fundamental. What's really inside these neutron stars? Just a dense soup of neutrons? Or does it harbor even weirder particles like hyperons, or even a sea of free quarks? The maximum mass a neutron star can reach before collapsing tells us how stiff this exotic matter is, how strongly it fights being compressed. Every massive neutron star found, especially one like Pulsar J09520607 so close to the edge, helps astrophysicists refine these complex models. Its crazy spin rate also tests our understanding of how stars evolve when they have a close partner, the Black Widow scenario, where a pulsar slowly eats its companion to spin itself up. Studying systems like this allows us to check and improve these models. And the fact that it inevitably collapses into a black hole? That's exactly what Einstein's theory of general relativity predicts for objects that get too massive in the strong gravity regime. Black holes were once just theoretical, but now we have tons of evidence they exist, from stellar mass ones like this new one, to the supermassive black holes at the centers of galaxies. Each one we find adds to our confidence in this cornerstone of modern physics. Plus, studying these extreme objects pushes our technology to the limits. Detecting faint pulses from distant pulsars or observing the dim glow of an evaporating companion star requires incredibly sensitive telescopes and clever data analysis. The Low-Frequency Array, LOFAR, that discovered Pulsar J09520607, and the Keck Observatory used to measure its companion, are at the cutting edge. The desire to understand these cosmic puzzles drives technological progress. The end of Pulsar J09520607 also reminds us that the universe is a dynamic, ever-changing place. Stars are born, they live, and they die, sometimes in truly spectacular ways. And black holes aren't just cosmic vacuum cleaners, they're a key part of how galaxies work. They influence star orbits, consume gas, and can even affect star formation in their host galaxies. The birth of a new stellar mass black hole is another small piece in this vast cosmic puzzle. Even though Pulsar J09520607 itself may have vanished behind an event horizon, what we learn from it sticks around. The data on its spin, mass, companion, and eventual, assumed, collapse will keep informing astrophysical models for years. Scientists will keep looking for more of these extreme pulsars, other Black Widow systems, and other objects on the brink of gravitational collapse. Every new discovery helps us build a more complete picture of the fundamental laws that govern our universe, from the tiniest scales to the unimaginably large. It's a journey of discovery, showing us both the awesome power of the cosmos and our remarkable ability to try and understand it. What a story Pulsar J09520607 has given us, right? Born in a supernova, spun up by eating its neighbor, becoming a record-breaking speed demon and the most massive neutron star known, it's been quite a ride for this star. Spinning 707 times a second, it was really pushing the boundaries of known physics, a testament to the extreme forces that shape our universe. Its colossal mass, too much for even the exotic stuff inside a neutron star to handle, led to its final, dramatic act, a collapse into the mysterious abyss of a black hole. A point of infinite density, hidden behind an event horizon from which no light can escape. So, even though its pulsed light has gone out, what it taught us shines on. Pulsar J09520607 has given us amazing clues about superdense matter, how stars evolve in pairs, and the absolute limits of existence for a star. It shows us again that the universe is a place of constant transformation, filled with objects and phenomena that boggle the mind and deepen our understanding of the cosmos. Studying these cosmic beasts is all about exploring the unknown, driven by our own human curiosity, our desire to comprehend this immense and awe-inspiring universe we inhabit. There's so much out there, so many secrets, but with every discovery like this one, we peel back another layer, revealing a little more of the incredible place that surrounds us. CTA, what other cosmic mysteries blow your mind? Let us know in the comments below. And if you want to explore more incredible stories from the depths of space and the frontiers of science, make sure to subscribe and hit that notification bell so you don't miss our next journey into the unknown. Thanks for watching.